Today we will go over the section 2.3, which is the product rule. Product rule is one of the many derivative rules that we talked about. So this one specifically differentiates the product of two functions. So let's say your px equals to fx times gx. That's the function given to you. Then if you want to take the derivative of that, you don't just do the derivative of fx times derivative of gx. It's not just a product of two functions. That's an important thing to note. When you're trying to take the derivative of it, you take the derivative of fx first, leave gx as it is, then you do plus, so sum them up, leave fx this time as it is, and take the derivative of gx for the second one. So here's a proof that why it's not just the product of these two functions. So let's say I have something like this where I expanded it like over here. Now when I'm trying to take the derivative of this, it would end up being here. But if I take the derivative of fx, I get 2x, and if I take the derivative of gx, I get 1. So if I do, like I said, derivative of fx and derivative of gx together, I'll end up with 2x, which is not what I'm supposed to end up with. My derivative for px is supposed to be like that. So px, derivative of px, does not equal to just derivative of those. When you're doing it, make sure you're following this formula right over here. Don't confuse it. So we did do proofs for other derivative functions, so why not for this one? So let's say, like I said before, I have px equals fx and gx together. Now if I plug that into my limits as I'm taking the derivative, I will go ahead and expand this part and this part here. When I expand this, that's what I'm gonna get. And over here, what I realize is I put the limits and they basically cut it as in like they put the fx out for this part, and they put the gx plus h out for that part. So when they did that, they ended up doing distributing the limits, which is one of the limit properties over here. So basically they just distribute it all over. They distribute it to, let me just erase this. So they distribute it to this part over here. They distribute it to this, and this, so to 4 sections, which you can see we have 4 limits. And when you do that, they ended up getting actually the derivative of fx, which is over here. Gx stays the same as it is, and then fx stays the same as it is, and then they ended up taking the derivative of gx, which ended up being the formula that we use. So for this question as an example, let's solve how to differentiate hx using the product rule. So if you guys watched the video 2.2, for a similar question like this, what we did before using the product rule was distributing these and expanding it, and then applying the derivative by using the sum rule, and then we used the constant multiple rule depending on what they gave us. But now, since we know the product rule, we don't have to do that. We can directly solve this. Remember, the product rule said if you have, let's say, hx, right? First, take the derivative of the first function, keep the second the same, plus keep the first one the same now, and take the derivative of the second one. So that is my formula. What I'm gonna do is I'm gonna say this is fx. Let me say that is fx, and I'm gonna say this is my gx. So let's try to solve it from there. I'm going to say h prime x is going to equal to take the derivative of the first one. So that's gonna come to x squared minus 3x prime. That's what I'm gonna say first. Keep gx the same, meaning x to the power of 5 plus 2. It's just the same, I don't do anything. Plus, keep fx the same, which is going to come to x squared minus 3x, and then take the derivative of gx, which is x to the power of 5 plus 2. I'm just going to put prime. Now, I can start taking the derivatives of the ones that I put prime to. So I'm going to say for the first one, I can use power rule for this, and I can use power rule for this. Remember, this is also aligns with the difference rule, meaning we have to apply the derivative to each one of these. We don't do it all together. So if I apply the power rule to that, remember my power rule was nx n minus 1, where my n is whatever is the power up here. So since my n there is 2, I'm going to bring that to the front, put the x here, and then I'm going to say 2 minus 1, which is 1. I'm not going to write it. Same thing with 3x. My n is actually 1, which is not shown over here. So keep the constant the same. Remember, this is constant multiple rule because I have a constant in the front. Keep the constant the same. Bring 1 to the front, which you don't need to write. X stays the same, but 1 minus 1 gives you 0. Therefore, this comes up to 1. So you don't really have an x, it's only 3. And that's the derivative. I keep the second the same, so I don't do anything to the second one. It stays the same. Plus, this I said was going to stay the same, so I'm going to keep it the same. Now I came to the second one, where this is the power rule, where I'm going to use the same thing I said over here, bring n to the front, which my n is 5 in this case, keep the x the same, do 5 minus 1, which is 4, and then plus, remember, whenever you have a constant, you're trying to take the derivative, it's just 0, so it's just plus 0, and then I keep going from there. So what I can do is I can expand these if you want to, or you can keep it the same, but let's just try to expand it. So I'm going to multiply these two, which I will get 2x to the power of 6. Now I'm going to apply just times by this and times by this, so I will end up having minus 3x to the power of 5 and plus 4x. Now I'm going to apply negative 3 times 2, which will give me negative 6. Now I'm going to do the same thing over here. If I expand it, like I'm just going to do it fast. If I expand it, I'm going to get 5x to the power of 6 minus 15x to the power of 5. Now I'm going to add these all together, so your answer is going to be 7x to the power of 6 minus 18x to the power of 5 plus 4x and then minus 6, and that's how we use the product rule. So what if instead of having two functions, which is px equals fxgx, you had three functions like this? It's easy when you think about the concept. What we did when I had px equaling to fx and gx, we said directly this would equal to, when you take the derivative, I take the derivative of the first one, keep the second same, and I'm going to say, okay, keep the first one the same now, take the derivative of the second one. Now if I expand this to 3, I'm going to say, okay, same formats, take the derivative of the first one, keep the other same, including the hx, now plus, it's the turn of the second one. So you can kind of think of it as in like the first one gets the turn, and then the second one gets the turn, and then the third one gets the turn. So what I'm going to do is keep the first one the same, take the derivative of the second one, like over here, but then I'm going to keep the last one the same too. So keep the other same. Now it's the turn of the last one, which I'm going to keep fx the same, keep gx the same, and then I'm going to take the derivative of hx. So that would be my formula. That's the expression for that. So whenever you encounter something like that, just do this. Even if you have a fourth function, like I don't know, like ex, something like that, it will continue like this. Take the other turn, take the other turn, take the other turn. Usually they're not going to give you a fourth or like fifth function. It's probably going to go max to 3. So keep in mind, this formula is also called the extended product rule because we're basically applying the product rule but extending it. So we might also say use the extended product rule, so don't get confused by the term. There's also another thing called the power of a function rule for integers. So remember what a power rule is. So let's say we express it in a way that x to the power of n, in this case it's u. So u to the power of n, whenever you have something like that, we brought that n to the front to take the derivative, and we did -1 like over here to take the derivative. However, in function notation, let's say instead of having u or x, you actually have a function inside, right? What do you do then? If you have a function inside and it's with a power of n, you apply the power rule in this case to take the derivative. So I brought the n to the front over here, like here, and then did -1. However, the one extra step we're going to do whenever you have a function inside is now, because this was kept the same, you take the derivative and multiply it again outside. So let's just try the examples that will make more sense. So for the first example that I underlined, I have the power of 6, and I can see whatever is inside is not just x. It's a function, it's my gx. So whatever is inside here, I'll do it with different colors. So this is my gx, and this is my n, right? Now over here, what I'm gonna do is I'm gonna say when I'm taking the derivative of that, I'm gonna bring whatever my n is to the front. In this case, it's 6. So I brought 6 over here. Now I can keep gx the same. So remember, my gx is x squared plus 3x and a plus 5. So that's the same. And then I do n minus 1, which is 6 minus 1. And then I take the derivative of gx, which is whatever is I underlined. So I'm taking the derivative of this over here. I use the power rule for the first one. For x to the power of 2, I can use the power rule and bring 2 to the front and do x. When I do 2 minus 1, it's just 1, I'm not writing it. Plus, I have 3 and an x. Remember, on this x, I have 1. So my power is 1. I can use the constant multiple rule. I'm going to keep the constant the same. Remember, even if I bring this to the front, it's just 1. And when I do 1 minus 1, it's 0. And x to the power of 0 is just 1, so I'm not writing it. When I'm taking the derivative of 5, when you're taking a derivative of any constant, it's just 0, so I'm not writing it either. So I took the derivative of this. So if I want to simplify, it comes up to 6x squared plus 3x plus 5 to the power of 5, and then I have 2x plus 3. If you want to simplify it even further, what you can do is multiply 6 by 2x and a 3, because this part is going to be confusing. You can't just multiply it because it has to the power of 5. So I can say y prime will equal to 12x plus 18 here, and then I can say x squared plus 3x plus 5 to the power of 5. So you can keep it like this. It's probably not going to ask you to expand further. So that is fine though. So that's how I use the power of function rule. So I want you to try this part and see if you get the same as me. So when I did it, I said my n is 4, like I did it right over here. I did it here. So I labeled whatever gx is and I labeled my n. So when I follow the formula right over here, I put my n, which is 4, to the front. I kept my g as the same. I did -1 to my n, and I took the derivative of gx. When I do it, I applied the power rule for this one and constant rule for this one, and I ended up with 2x. If you want to expand it further, you can just say 8x and then x squared minus 3 to the power of 3, and that would be your answer. For this one, it wants us to use the product rule to differentiate this function specifically. So you can see this is not really in the format of a product rule. This is x minus 3 over x plus 3. But what you can do before applying product rule is change this into product format. So what I mean by that is do fx equals to x minus 3 and then times x plus 3 to the power of negative 1, which means the same thing as saying x minus 3 times 1 over x plus 3, which is when you do it, you will end up getting the same thing. So now I can apply the product rule, and I'm going to say this as my fx, and I'm going to say this as my gx. So when I do that, I can actually apply the product rule now. I'm going to say fx, where I take the derivative of fx, so take the derivative of x minus 3, right? Gx stays the same, so x plus 3 to the power of negative 1, plus keep fx same, so x minus 3, and now take the derivative of gx, which would be x plus 3 to the power of negative 1, but put prime. So now I'm going to actually take the derivatives for fx that I put in gx. So when I do that, my x minus 3 would come out as just 1. Why? Because I have x to the power of 1. We said if I use power rule for this, bring n to the front, I have 1, and do minus 1 over here, I have x to the power of 0. What's x to the power of 0? It's just 1. Okay? And minus 3 in this case over here is just a constant, would come to 0. Now I'm going to keep going. I don't apply anything to this, so x plus 3 to the power of negative 1, plus I don't apply anything to this either. Now I take the derivative of this one. This one is the rule I talked about. So I'm going to erase this. This one is the rule I talked about. So here is my gx, but I'm just going to call it hx because previously it was in gx form, but I'm going to say hx, where I have the negative 1, which is in a power. So I'm going to bring this negative 1 to the front, keep hx the same, and do minus 1 to here. So minus 1 would give me negative 2. But now I'm going to take the derivative of inside because it's not a number, it's a function. So when I take the derivative of x plus 3, it would be 1 also because it's the same thing as this one, this part over here. So x to the power of 1 is just 1, and the constant 3 would just come to 0. So now I have everything. I'm just gonna write it, simplify it. So x plus 3 to the power of negative 1 is just 1 over x plus 3. Plus I have x minus 3 times negative 1 over x plus 3 to the power of 2. So now from here what I can do is multiply these two also. So when I do that, it's going to come to 1 over x plus 3 times plus, sorry, so I have plus and then negative, so I'm just going to put it in brackets, so negative x minus 3 all over x plus 3 to the power of 2. So from here, what I can do is I can add them together. So also remember this is in brackets, okay? So what I can do, if you guys are confused about this plus and this negative goes over here with these. So what happens is I end up with 1 over x plus 3, and then I will end up with plus, I'll just put it in brackets, I have negative x and a plus 3 when I do that, and x plus 3 to the power of 2. So now I can add them together, but I see that I can't really add them because their denominators are not the same. To make it same, I can multiply this by x plus 3 and then add them together. So now I'm left with this where I can actually add them together. I see that I have a positive x and a negative x when I add them together, so those cancel out. So I'm left with 6 over x plus 3 to the power of 2, and that would be your answer. So how do you know when to use the product rule and when to not? So there are cases when it's not very appropriate, appropriate meaning it's not necessary. Like you can use the product rule in some cases, but it would just be long and unnecessary when you can use the other rules that we learned. So let's say when one of the factors is a constant, or when it be easier to first determine the product of the factors and then use the other rules to determine the derivative, those are the cases you don't use product rule. So let's say I have gx, which equals to x plus 1 and an x minus 1. Now if you use product rule for this, it will give you a longer way than you just saying x squared plus 1, minus 1, sorry, x squared minus 1, and then take the derivative from that. Why would you use product rule and use the long way instead of just distributing these and opening it up and it would be x squared minus 1? Take the derivative of that from power rule, it would just going to be 2x. That's it. Another case would be, let's say you have fx equaling to 3, which is a constant like I told you guys, and then x squared plus 1. In this case, again, you can just distribute it. Why would you use the product rule? I can literally say 3x squared plus 3 and then just use power rule, constant multiple rule for this, and just get the answer 6x. That's it. So for these, just don't even bother using product rule, but if it's more complicated, then that product rule is there to make it easy for us. A 71-liter gas tank has a leak. After T hours, the remaining volume V in liters is given by the function. Use the product rule to determine how quickly the gas is leaking from the tank when the tank is 60% full of gas. So to understand what it's saying, the situation is I have a tank that the total volume is 75 liters, right? And it starts to have a leak. This equation represents the remaining volume in this tank. So my y point represents the volume where it's like it decreases by t hours. So when the time passes, the volume will decrease. So it wants us to use the product rule to determine how quickly the gas is leaking. That's what I'm trying to find. So you can say that because this is the equation that represents remaining volume, taking the derivative of that will give us how quickly the gas is leaking. But it wants us to find that at a point when the tank is 60% full of gas. So my y point I'm going to use is actually going to be, since the tank is 75 liters, I can find 60% of 75 liters, and that would be my y point. So I found that 60% of the total volume is going to be 45 liters, so that's my y point. So now what I can do is put this 45 as a y point over here and find the time at that point, because time is not going to change when you even take the derivative. Our time is going to be constant. So if I find the time, I can actually find how quickly the gas is leaking if I plug that time back into the derivative. First thing I'm going to do is divide both sides by 75. Now because this is in square, I can actually take the root of both sides to get rid of that. Now I can actually put this a positive 1 back here as negative 1. And now I'm going to multiply both sides by negative 24 in order to get rid of this, so I'm left with t. So I'm going to also multiply this by negative 24. But before I do that, I'm just going to plug this into my calculator and then multiply by 24. When I plug it back into my calculator, I found that my t is 5.41 hours. So now only thing left is actually taking the derivative and then plugging this t value back into there. So when we're taking the derivative and using the product rule, I have a constant in front, which I'm going to leave it as it is. my n value, which is 2, comes to the front. So I'm going to do times 2. This is gx. Because it's a function, we leave it as it is, but then times it by derivative on the outside. So I'm going to leave it as it is, so 1 minus t over 24. And then we remember that to the n value, we do minus 1. So it's 1. And then I times it by the derivative of gx, which would be, if you think of it, I'll do it right over here in a different color. I have 1 minus t over 24. If you take the derivative of this is a constant. Taking the derivative of a constant is just 0. So now I have negative 1 over 24 times t. You can think of it like that. T has a power of 1. So remember that we did it before. If you bring this 1 down and do minus 1 over here, it's just t to the power of 0, which is 1. So it doesn't matter. All that happens is constant states, and then t is just gone. You don't have to write it. So my derivative that I'm gonna times it by is the value of negative 1 over 24. Now I'm left with negative 6.25, 1 minus t over 24. Now I can go ahead and plug 5.41 hours back into here. So when I do that, I get the value, the answer of negative 4.841 liters per hour. So that would be my answer. So determine the slope of the tangent to the given function at x equals negative 2, and then we need to explain how to find the equation of the normal at that point. So first thing you realize is what we're trying to find is the slope of the tangent, which just means take the derivative. And taking derivative of this given function is the only different part, because I have 3 different functions. So this would be my fx, this would be my gx, and that would be my hx, but I don't want to say hx, so let's say tx. I don't know. You can say anything, but 3 different functions you can see over here. So that means we are applying it, applying the extended power rule from previous slides. So if you forgot about it, you can go back and watch it. But it's in this video anyways. So what happens is, when I'm gonna start by taking the derivative of that and then plugging in the value given. So when I'm taking the derivative, we said for extended power rule, what we do is take the derivative of fx, keep the other one same. So I'm gonna do that. When you take the derivative of 2x, remember power of x is just 1, so it's just gone, and only thing I have left is 2. I write the other ones as it is, so x plus 1 power of 3, and then x squared plus 2x plus 1 squared. Then I do plus, and then take the derivative of this, keep the other one same. So I'm gonna leave 2x as it is. Taking the derivative of that is applying the power rule. I'm gonna bring 3 to the front, so 3 goes here. Because this here is a gx, it stays as it is. Do minus 1 to the n value, so I'm left with 2, and then take the derivative of gx inside and times it by it. So what I see is x to the power of 1, which would just become 1, and the constant plus 1 is just 0 when you take the derivative. So you don't even have to write it, but it's just times 1. And the other thing, just we leave it as it is. We don't touch it. And we do plus again. Now I keep 2x as it is, I keep this one as it is, and I take the derivative of this. It gets confusing over here, so I'm going to erase it. So I'm taking the derivative of this now, keep the other one same. So 2x, x plus 1 to the power of 3. When we're taking the derivative of that, don't forget the n comes to the front. So I'm going to do a bracket. So 2 is in the front because that's my n value. Keep inside same because it's a gx value. Do minus 1 over here, which you're just left with 1. And then times the derivative of gx. So now when I'm taking the derivative of gx, I see that for x squared, use the power rule, bring 2 to the front, x, and then when you do minus 1, it's just 1. When you do it for 2x, it's just plus 2, which is the same thing we did over here with the 2x. and then 1 is just a constant, so I'm left with 2x plus 2 as a derivative. So what I can do now, instead of like trying to distribute it, I'm just going to plug in -2 my x value when I'm rewriting it. When I do that, I get something like this, and all I'm going to do is either plug into your computer or just do it. So what I'm going to do it with you guys. So I have 2 here, and then -1 to the power of 3, because it's just because -1, it's just going to be -1 times -1. Now inside I have -2 to the power of 2, which is just going to become 2, positive 4, sorry, positive 4, and over here is just going to be -4, which is going to cancel each other out, so I'm not even gonna write it. And then I have 1 to the power of 2 is just 1, so I'm not gonna write it either, so my bracket is just basically gone. Now I'm on to the blue side. Over here is just going to be -4. Inside I have -1 to the power of 2, which is just 1, so I'm left with 3. Over here it's the same idea, positive 4, -4. You don't even have to write it because it's gonna become 1. And then to the purple side I have -4 over here, even though I had positive sign over here, because I have negative, it's -4. Over here -1 to the power of 3, so I have -1 times -1. For the brackets, I'm just gonna write 2, and then inside is just positive 4, -4, it's gone, and then 1, so I'm gonna write the 1 just in case, times -4 plus 2 is just going to be -2. Now if you solve this, what you're gonna get is -2, -12, and a plus 4, and inside I'm just gonna write it as -4, so that's just gonna give you -14, -16, and your answer is just going to be -30. So now if you want to find the equation of the normal at the same point, we can start by what we have in order to find the equation. So equation is in this format, and right now my m, what I found for the slope, not for the normal, for the tangent, is -30. To find the slope of the normal, what we do is find the negative reciprocal of the slope of the tangent. Negative reciprocal of this would just be take the reciprocal and take the negative. Because it's already negative, it just turns into a positive. So 1/30 is my slope. So I can just write it down as y minus y0 right now, 1/30, and an x minus x0. But what I realize is, even though my x's are the same, so x -2, so my x, my point x is -2, I see that I don't know my y. In order to find the y value, what you need to do is plug in that -2 into the original equation so you can find what's my original y value. So when I do that, I'm left with -4 over here times -1 to the power of 3 is just -1, and in the brackets I have -4, plus 4, -4, which is 0, and then I'm left with 1, so it's just 1. So -4 times -1 is just going to give you 4. So my answer for the normal, the equation of the normal, is just going to be y minus 4 equals 1/30, and then x plus 2. And remember, I did plus 2 because in the equation it's minus, and since my actual x is -2, it just becomes positive 2, in case you guys got confused. So that would be my answer for the equation as well. Thanks for watching. If you have any questions, make sure you ask them by going to our website. We have a form section where you can ask any of your problems and we will answer it.